Hi Chem 110H, Dr. Bevilacqua here. I'd like to do a quick screencast on Homework 4 Problem 9, which was collected with Homework 5 set. And this question was about the last term here in the van der Waals equation, which is the correction to the ideal gas equation for molecules interacting, which subtracts or decreases the total pressure. And the question was, why does this term go as the density of the gas squared, rather than to the first power or the third or a fractional number like 2.7. So a simple way to think about it, but perhaps not having the most insight, is to remember that if we have two copies of, let's say, A interacting to make a dimer A2, which we can think of as 2A going to A2, we can remember that we write down the rate law for this as equal to the rate constant for the process K times the concentration of A squared. And that too is perfectly analogous to that too. But let's see if we can get better molecular insight into the problem. If we consider two atoms of A coming together to make a dimer, we can think about the number of combinations for this to happen. And in order to do that, let's consider four different molecules, four different copies of this, and how many combinations we can have. Well, we know that if we take all four and we multiply them together, we'll get 4 squared, or 16 different cells in our grid here. We know immediately that we can't get dimers out of a molecule interacting with itself, so we'll go through and we'll eliminate all of those possibilities by putting an X along the diagonal. We also know that if molecule 1 interacts with 2, that's the same as this combination of 1 with 2. So we don't want to overcount, so we'll go ahead and cross out all of the cells that are above the diagonal. That leaves us with these ones here, which are unique dimer combinations. I put a check mark there for them. And then what is the math that we can use to generalize to figure out how many such cells that we have? Well, we can look at this and we can see that the number of check marks is almost n squared, but it's n times n minus 1, where we've subtracted out the diagonal, and that's where the numerator comes from. That would give us all of the cells except for the diagonal, but then we need to throw half of them away so that we don't double count, so we divide by 2. In general, there are many copies of molecules, Avogadro's number, so 1 is vanishingly small, so we can approximate this as n squared over 2. The 2 can be absorbed in the proportionality constant, and so now we can understand where the 2 comes from in the correction to the van der Waals equation. It comes from the number of combinations of two molecules, unique combinations of two molecules. And this is a nice combination or probabilistic insight into chemistry, and it's something that appears over and over again in chemistry, and it leads to an entire field referred to as statistical thermodynamics or statistical mechanics, because it looks at combinations and probabilities. Thanks for listening.